In the previous video, we introduced context mixing and discussed its importance for understanding how transformers process data and build contextualized representations. We also talked about why self-attention weights alone are not a reliable measurement of context mixing. In this video, we look at some of the proposed methods that expand the scope of the analysis beyond self-attention for quantifying context mixing. Attention rollout is a context mixing technique that relies on the multi-head attention module, but instead of focusing on a single layer, it looks at how attention weights accumulate and changes across layers. Consider all the attention weights in the model as a graph. When token A attends to the token B itself has already attended to a set of other tokens in the previous layer. Attention rollout multiplies these weights across layers to consider all possible paths in mixing information. However, this method has two drawbacks. First, it makes a simple assumption that context mixing relies on 50% on the context and 50% on the residual connection, which is not necessarily the case. Second, it considers only attention weights, neglecting the impact of other components in context mixing. Another technique called attention norm was proposed to consider the effect of the value vectors as well. The idea is that sometimes the token that receives a large amount of attention has a small norm for its transformed value vector. So when we multiply these two things together, the contribution from that token wouldn't be significant. In other words, a higher attention doesn't necessarily lead to a higher contribution to the final representation. ALTI and Gelobeng are two other variants of norm-based scores that aggregate scores over layers using the rollout method. Gelobeng additionally incorporates the effect of the layer normalization into the computation as well. Interestingly, this method can reveal that the weights of the first and the second layer normalization actually cancel out each other, which is another reminder for us why we need to consider the effect of all components when measuring context mixing. Value zeroing is a measure of context mixing that considers all components within a transformer layer. To measure how much the token I depends on the token J in a sentence when forming its representation, value zeroing replaces the value vector associated with token J with a zero vector. This provides us an alternative output representation for the token I that has excluded token J in the mixing process. So by measuring the distance between the alternative output representation and the original one, we can quantify how much the output representation I is being affected in the representation space in the absence of token J. In contrast to general perturbation-based methods, value zeroing doesn't update the input token representation from a layer input. It only nullifies the value vector of a specific token, keeping the pattern of the attention flow intact in the model.
Let's compare these different methods with each other and see how they work in practice. Consider the task of subject-verb agreement, where the language model is fine-tuned to replace the masked word with the right verb with the right number. For example, in the sentence, the pictures of some hat were scaring Marcus. If we mask the main verb, the model has to choose were instead of was. If the model chooses the correct verb form, the contextual representation it builds must rely heavily on the number of the main noun in the sentence. Here we see patterns of context mixing for a specific intermediate layer of the model based on different methods for this example, which is correctly classified by the model. As we can see, attention scores highlight the special token of separator, while we can see a more plausible pattern in the scores of more advanced methods when we cover more model components in the computation of context mixing. For example, value zeroing correctly mostly uses the information of the subject, the word pictures, for detecting the number of the masked word. Next, we aggregate scores across all layers in the model to have a global sense of context mixing. The darker color indicates more influence of tokens on building the representation of the masked token. Using value zeroing scores, we can see the model actually properly uses the subject to form the representation of the masked word. In this video, we learned about some methods to measure context mixing in transformers, and we saw that attention is not a good metric for such purposes. These methods focus on representation space without relying on extra output classifiers. In the next video, we'll explore other types of transformer-specific methods that involve the model's decision and find subnetworks in the model that are responsible for performing specific subtasks.